Hello everyone, welcome back to another pre-calculus video. In this video, we are going to look at parametric equations. So parametric equations is a way to describe motion in terms of another parameter. Usually we're thinking about with respect to time. So if we have a rock and we want to throw it off of a cliff, it's going to make this parabolic motion, right? We can model it in terms of a parabola that opens upside down. Before we were able to talk about that horizontal distance and we could talk about that vertical distance. But now we're able to talk about how long was the rock in the air? At what point in time did the rock hit the ground over here? So that's what we're looking for in this section. So when we see parametric equations, we're going to see it modeled with two equations in terms of a horizontal distance and then a vertical distance. And we're going to think about those distances with respect to time. So parametric equations for us are going to come in pairs. You could do this in 3 dimensions with 3 equations, which we'll talk about in a later course. So that variable t is called the parameter. When we draw a set of parametric equations, we always want to think about orientation. Orientation is the direction. So think about if we have a particle that's moving along some kind of graph, how is that particle moving? And that orientation is going to show us that. And we can show that when we draw a picture by looking at these little arrows. So usually what happens with a set of parametric equations is that you have a set and then you have some kind of restrictions on t. Okay, sometimes t is restricted between 2 values, maybe like 0 to 3. So we're thinking about that time from 0 seconds to 3 seconds. Sometimes you may want to think about it in terms of it going on infinitely. So you could have an infinity over here. Okay, but typically what happens is we have a restriction on t. Think about that rock again as we throw it. Time's not going to go on forever because at some point it's going to hit the ground and then it's just not going to move again. So we would restrict that time for how long we want it to be in the air, or how long it actually is in the air, depending on the scenario. So let's look at a few examples. We're going to start with number 7. We'll do a couple of these. So what's happening here is we've got a set of parametric equations. We are going to graph these by hand. Then I'll show you how to use Desmos to graph it. And we want to show the orientation, and then we're going to find a rectangular equation for the curve. So number 7, they tell us x is equal to 3t plus 2, y is equal to t plus 1, and we're restricting t to be between 0 and 4. So let's start with finding that rectangular equation. To figure out the rectangular equation, what we want to do is solve one of these for t and then plug it into the other one. So I'm going to take x equals 3t plus 2, and I'm going to solve this for t. I can do that by subtracting 2 and then dividing by 3. And then we're going to substitute into the other equation. So we had y equals t plus 1, but we've got an equation for t. So we have x minus 2 over 3 plus 1, and then we can simplify that. We can split that numerator and then combine like terms here. Negative 2/3 plus 1 is going to be a 1/3, and we could rewrite that a little more concisely this way. So this guy is actually a linear equation. Now, we could have done that the other way. We had y equals t plus 1. We could have solved this one for t and then made a substitution into the other equation. X equals 3t plus 2. Y minus 1. Substitute in. And it's going to give us the same equation if we were to solve this for y. So let's go and do that. So x equals 3y minus 1. So to solve for y, we would add 1 and then divide by 3. So you see, you're going to get the same equation either way. You can approach it from either side. But the goal is to solve one of the equations for t and then substitute into the other equation. So that's how you get the rectangular equation. But we need the domains to match. So we've got this linear equation here. Normally, a linear equation goes on forever and ever. The domain is all real numbers, but there was a restriction on t here. T is bounded between 0 and 4. So we only care about this model when time is between 0, maybe this is 0 seconds and 4 seconds. So what would that look like in terms of our domain? Well, to figure that out, we're going to think about creating a table. So t was bounded between 0 and 4. So I'm going to use whole numbers between 0 and 4. And we're just going to substitute these in and find the xy ordered pairs, and that will be really easy for us to graph. So if we plug 0 in, 3 times 0 plus 2 is 2. Plug 1 in, 3 times 1 plus 2 is 5. Plug 2 in will give us 8. Plug 3 in, and then plug 4 in. We're going to do the same thing for the y coordinates. Plug 0 in, we're going to get 1. Plug 1 in, we're going to get 2. Then 3, then 4, then 5. So we've got these XY ordered pairs from these two columns. So we could draw a picture. Y's are going from 0 to 5. X's are going from 2 to 4. So our domain here, remember this is a linear equation, and it's increasing, right? Because we have a positive slope here. So our domain's going to go from 2 to 14, and that's inclusive. And our range is going from 1 to 5, inclusive. So this equation will work as long as x is between 2 and 14. So let's graph what's going on now. So at 2, y coordinates 1. At 5, the y coordinates 2. At 8, we are at 3. At 11, we are at 4. And then 14, we're at 5. So then we're going to connect the dots. Now, we only need this piece of the graph. Okay, normally with a line you do this, right? But that is not correct. We cannot do that here because this line's not going to go on and on forever. It's got a domain restriction. Okay? And that domain restriction is between 2 and 14. The reason it's got a domain restriction is because the t's had a domain restriction here. So there's our graph. But then we need to show orientation. So this was our first point, this was our second point, third point, and so on. So it's going to the right, so we can show orientation that way. So let's try another one. And this is where you may want to pause the video, try it, and then come back and check your answer. So for the one to try number 19. So let's look at this one. We have x equals 2 cosine t, y is equal to 3 sine t, t is restricted between 0 and 2 pi. Let's start by finding that rectangular equation. So this one's going to use a trick. So we can rewrite that first one. X over 2 is equal to cosine of t. And that second equation, we can solve for sine of t. And the reason we want to do that is because we have an equation that ties all that together. We know that sine squared plus cosine squared is equal to 1. So that's what we're going to use as our big substitution there. This one we're not solving for t because then we have inverse cosines, inverse sines. There's a much easier way to think about this. So we've got a substitution for cosine and for sine. We're going to use that. My pre-cal teacher called it the 5-star general because A lot of things are derived from it. And we're going to substitute in. So sine was y over 3. Cosine was x over 2. So we have y squared over 3 plus x, y squared over 3 squared, which is 9, plus x squared over 2 squared, which is 4, is equal to 1. And usually we think about these written this way. This guy is the equation of an ellipse. All right, so let's see if we can figure out orientation. So we're going to create that chart like we did in the last example. So we're going from 0 to 2 pi here. So I'm going to pick some nice values for sines and cosines. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. That'll get me there. So substitute everything in. 2 times cosine of 0 is going to be 2 times 1, which is 2. 2 times cosine of pi over 2 is going to be 2 times 0, which is 0. Plug pi in, we're going to get a negative 2. Plug 3 pi over 2 in, we're going to get a 0. And then plug 2 pi in, we're going to get a 2. Now we're going to figure out y coordinates. Plug 0 in, 3 times sine of 0 is 0. Pi over 2, 3 times sine of pi over 2 is 3. Plug in pi, plug in 3 pi over 2, plug in 2 pi. So remember, these are x, y ordered pairs. So we're going to think about our graph here. So notice that our x's are going from negative 2 to 2, and the y's are going from negative 3 to 3. So our first point is going to be at 2, 0. Our next point is at 0, 3. And then at negative 2, 0, and 0, negative 3, and then back around. So our ellipse, and you'll have to use your imagination a little bit to get that round figure, but it's going to look like that. So orientation-wise, we're starting at 2, 0, and then we're moving to 0, 3. So you can see how this is moving counterclockwise around the graph, and it's making one loop around that graph. So there's our orientation. Now, if we wanted to graph these in Desmos, so I'm going to graph that first one that we did. We're going to write it like an ordered pair. So we have 3t plus 2. That's our x. And then we're going to do our y was t plus 1. This was the first one that we did. And so you can see how it recognizes, hey, this is going to be a parametric equation. And we just got to tell it restrictions on t. So there's our linear function that we came up with. Desmos is not going to show you orientation. Okay, if we do the other one, same kind of thing. It was 2 cosine of t and 3 sine of t. And then we went from 0 to 2 pi. So you see that ellipse coming out.